So this is fourth week live session, and okay, before we start, do any of you have anything to say? Okay, if not, so so what we did last time was quantization of complex Klein-Gordon field, and so we also derived the energy momentum tensor, if you recall. So from the energy momentum tensor we have seen how to get the Hamiltonian density, right? So Hamiltonian density was, so let me write down the energy momentum tensor. So this was our energy momentum tensor, and we saw that T00 is nothing but the energy density. Okay, this we derived actually for the Klein-Gordon Lagrangian, and then we said that T0I is nothing but the momentum density. Okay, and if we integrate this over space, the entire space, we get momentum operator. So T3x, T0I should give us the momentum operator along ith direction. So what we will do today is find out this momentum operator for the Klein-Gordon field. Okay. So let us do that. So what was the Lagrangian, Klein-Gordon Lagrangian? Can someone say what was the Lagrangian? Because we did so many things with Klein-Gordon Lagrangian, you should know now that what is the Lagrangian.
Dou mu phi plus n square phi square equal to 0.
Yeah, so that is the Lagrangian. So so that means this is equal to dou mu phi, and okay. So when we write down T0I component, this term will vanish, and we get T0I will be equal to del 0 phi. Okay, so that means the operator I'm writing the three-dimensional operator instead of writing ith component. So it would imply that T3x, this is phi dot, right? Phi dot, and that is gradient of phi. If you have any difficulty in any of the steps, do let me know. Okay, and what is phi dot? Phi dot is nothing but conjugate momentum pi. So conjugate momentum is defined as del phi dot so this is equal to half phi dot square minus half gradient of phi square minus half m square phi square. So this is equal to phi dot. So therefore the momentum operator is d3x pi gradient of phi. Okay. Everything is good till this point. Okay. Now recall what was the field operator and the corresponding conjugate momentum. So we did the quantization in our second session. So there we wrote down quantization of real Klein-Gordon field, I mean. So phi of x was equal to d3p over 2 pi cube 1 over square root 2 EP, the annihilation operator exponential of I p dot x plus a dagger exponential minus I p dot x. Okay, and the momentum operator was defined like this. Okay, since we need gradient of phi, let me compute that also. So gradient of phi will be equal to, so gradient will hit these exponentials and that will give us IP from the first term and minus IP from the second term. So this is equal to one over minus a dagger p exponential minus IP dot x. Okay, and recall the momentum operator as well. Where EP, remember EP was the square root of p square plus m square. I think in our previous sessions we wrote EP to be omega p, but sorry, the normalization here is minus I square root of over 2 minus okay. So now let's compute this particular operator. So P is equal to integration d3x. Let me write down the expression again, pi gradient of phi. Okay, so integration d3x d3p prime over 2 pi to the 6 and 1 I coming from this gradient of phi and minus I coming from this pi operator. So that will become plus. Okay, and using p index for p variable for pi and p prime for gradient of phi. So we have half square root of EP divided by EP prime okay, then pi is, so let me just copy this portion. Okay, and gradient of phi ap prime exponential of I. Okay, remember there was this p vector as well, so we have p vector outside, exponential I p dot p prime dot x minus a dagger p prime minus I p prime dot x. So let us see what we get. We will get 4 terms, and then we need to use the properties of Dirac delta function. d3p prime divided by 2 pi to the power 6 half, I'm taking outside, p plus p prime dot x minus a dagger p a p prime exponential minus I okay, then ap a dagger p prime p minus p prime dotted with x, and the last term is exponential minus I p plus p prime. Okay, now so this term along with this integration over d3x will be replaced by the 3-dimensional delta function p plus p prime. Okay, likewise this term, that and that one. So let's do that. So we get half of d3p prime. Since from those delta functions we will also get a 2 pi cube factor, so we will be left with 2 pi cube here. P prime P plus P prime minus a dagger P Okay, now let's take this integration over d3p prime. So that will give us, so for this term, first term, p prime will be replaced by minus p. So keep p outside. Since p prime will be replaced by minus p, but e p prime is square root of p prime square, so that doesn't get affected and these two gets cancelled out. Okay, and we will be having, so this is ap a minus p Then for this term, A dagger P, A minus P. Okay. For the third term, sorry, for these two terms, P prime will get replaced by P, right? Then only this, so this will give non-zero contribution only when P equal to P prime. Likewise, this is also giving non-zero contribution when P equal to P prime. So we have A dagger P, AP minus AP, A dagger P,
I have a doubt. You said it gets cancelled out, right? So P is equal to minus P in this part, in the first term. Can you explain that part again?
Yeah, because see here we have exponential I P plus P prime. So that is what is giving us this three-dimensional delta function evaluated at P plus P prime. So this will give non-zero contribution only when P plus P prime equal to 0.
Oh, right. Okay, got it.
Yeah, so when we take integration over d3 P prime will be replaced by minus P.
Yeah, got it.
Yeah, and for these two terms, P prime will be P, again for this one, P prime will be minus P. But I'm worried why I'm getting a minus here. Let's see. Hopefully I'm not making a mistake. Plus A dagger P, A dagger minus P. Okay. Now note that these two terms are actually, when integrated over d3p, will actually be 0. Why? Let me just explain. So this is minus infinity to plus infinity d3p. Let me not write down the, okay, so 2 pi q p a minus p. So this is equal to so if I, let's say I'm replacing p vector by minus p prime, because it's dummy variable, I can always do that. So we'll get minus d3 p prime, integration limit will be exchanged, so infinity to minus infinity. You can also see, I mean, it is actually odd, so integrand is odd, so that's why it will become 0, but you can see explicitly. So this is minus p prime a p prime, okay, and you know that a commutes with itself, so that's why the operator we can write, so this becomes d3 p prime, this we can rewrite as a p prime, a minus p prime, and in order to change the integration limit we get a minus sign, so d3p. Now since p prime is a dummy variable, I can always choose to write it as p. So you see the left hand side is equal to minus of itself, so that's why that integration is 0. d3p over 2 pi q this is equal to 0. Okay, likewise the same reasoning will apply for this particular term, fourth one, so that will also be 0. So let me just write down d3p a dagger p, a dagger minus p.
Can you please go scroll up?
Yeah.
Here. How does the operator get changed its place?
Which step? This one?
Last step here.
Yeah.
Minus p is at first.
Yeah, because the commutation relation for the creation and annihilation operators is AP, A dagger P prime, that is equal to that is equal to 2 pi q delta 3 p minus p prime. Okay, and AP and AP prime always commute. Likewise, A dagger P prime. So that's why, since we have A operator, I can always switch these two because they commute, right? So A minus
So
P prime.
you consider minus p prime as q. So
Yeah.
okay.
Yeah. Okay. So then those two terms are not there, and what we are left with, P is equal to half of d3p over 2 pi q p minus of okay, and now we can use that commutation relation. So AP, A dagger P commutation is nothing but 2 pi cube delta 3 P minus P, delta 3 is 0. So this implies that A dagger P is nothing but A dagger P AP, okay, plus 2 pi cube delta 3 at 0. So this implies that P operator, okay, now I remember where I have missed one minus. See here, so this was T mu, but when we are writing both indices in the contravariant position, here we have del contravariant I acting on phi. So that means this is minus of gradient of phi. Okay, because remember our convention. Our convention is del mu covariant is del t comma gradient, and del mu contravariant is del t minus gradient. So that's why from here, when we replace it as gradient, we get a minus sign. So there is a minus sign here, so that minus sign will follow. Minus okay, so these two are plus. Okay, and now I am replacing A dagger to be A dagger A. So that half factor will get cancelled out over 2 pi cube P vector A dagger A. And this is infinity, which we will again neglect the way we neglected for the Hamiltonian as well. Okay, so that is the momentum operator. So you can explicitly check that momentum operator acting on this state P will give you P. Okay, we can see that quickly. So this is, so the left hand side is d3p over 2 pi cube p vector okay. And what was the definition of state P? It was square root 2 EP a dagger, sorry, let's use a different variable for P operator, and then this is EP a dagger P acting on 0. So that is the state. And what you can do is apply the commutation relation between A and A dagger to rewrite it as P prime A dagger P prime. A dagger is again A dagger A plus 2 pi cube delta 3 P minus P prime acting on the vacuum. So this term will give you 0 because here A is acting on ground state. So that is 0, and from the second term you get integration d3 p prime, 2 pi cube gets cancelled out, p prime a dagger p prime delta 3 p minus p prime acting on 0. So p prime will be replaced by p, and we are left with p square root 2 EP a dagger p acting on 0. Okay, and that is nothing but the state P. Clear? Okay. Okay, now next what we can do is so okay, you have been taught the propagators, right? Are those things clear? Feynman propagator.
Yeah.
Okay, someone is saying no. So Dipti, what all things were covered? Can you just tell me briefly? Like Feynman propagator and what else? Retarded propagator also?
Yeah, 1 second.
Those contour integrations and all, I think was discussed in the lecture, but since one person said it was not clear, I will explain.
Yeah, I think it would be, I can tell you what was covered, but it's better if you could give it to us in a more palatable way.
Okay. Okay, good. So, okay.
So just a second, I'll just tell you what was covered. Yeah, so the spin half particles propagator I by q bar minus m, that one, and I by q square minus m square, and the photon propagator.
Okay. Okay. Fine. Fine. So before we get on to the propagator, let me tell you one more thing. So if you look at these operators phi and pi that we wrote down in order to quantize our Klein-Gordon Lagrangian, so we have written it down here. So do you notice one thing, that although we started with a Lagrangian which was Lorentz invariant in the sense that it has time dependence and spatial dependence, but in order to write these operators down, phi and pi, we only wrote them as a function of the space but not time. So which means the operators were written in Schrodinger picture where operators are time independent. But in order to get those propagators and all, what we want is a completely Lorentz invariant picture. So before we get on to propagators, let me show you what will be the corresponding Heisenberg operators, okay, for this phi and pi. Okay. So you all know that Heisenberg operator is exponential IHT, Schrodinger operator exponential minus IHT. Now, okay, but for the operators that we have, the field phi, we will not write down this h in the subscript, but when we write down phi x, that means phi is, the argument is not actually x vector, 3 vector, but it also contains, so this is nothing but phi x comma t, okay. So this means this is the corresponding Heisenberg operator, okay. So in order to get the Heisenberg operator, what we actually need is exponential IHT AP exponential minus IHT. What is the value of this particular, what will it be? Okay, so let's remember the commutation relation between Hamiltonian and the annihilation operator. So what was Hamiltonian for our Klein-Gordon field? Hamiltonian was d3p over 2 pi q EP A dagger A. You all agree? So the commutation relation between the Hamiltonian and the annihilation operator is equal to d3p prime over 2 pi q EP prime, commutation between sorry, was there any half? I guess no. Yeah, no, there was no half.
Can you please explain the last 3 steps?
Okay, so what we are doing here is trying to find out the corresponding Heisenberg operator of the Schrodinger operators that we wrote down, and in order to do that, we have to find this thing. And why we need to find that thing, let me also tell you, because probably the motivation is not clear. So phi Heisenberg will be equal to integration d3p over 2 pi q square root 2 EP exponential IHT minus IHT plus exponential IHT A dagger P exponential minus IHT. Sorry, this was plus. Okay, that's why we are figuring out this particular operator right now. In order to do that, I have written down the Hamiltonian that you already derived for our Klein-Gordon field. And so Hamiltonian and AP, they do not commute, but there is something on the right hand side. That's what I'm trying to figure out right now. Okay. So in the last step, I'm not doing anything extra than writing down this Hamiltonian here, and then AP is already there. Clear? I mean, maybe you are getting confused, so I can also write it down this way. Is this fine? Now, since they will not contribute in the commutation relation, we can always keep them outside. So T3P prime over 2 pi q EP prime, commutation relation between AP prime, AP prime dagger AP prime and AP. So you will get this is nothing but minus of 2 pi q delta 3 p minus p prime, that commutator. So then this is equal to, sorry, there is a 2 pi q as well coming from that commutator. So this is what? This is EP. 2 pi q gets cancelled out. EP. Okay. Likewise, we can find out what is the commutation between H and A dagger. And this resembles the commutation you know from your quantum mechanical harmonic oscillators, the same commutation relation you are obtaining here. And this will be, let me just go over it quickly. So again, the same thing. A dagger A with AP dagger. Okay, so you will now not get the minus sign because now the commutation is A dagger. So 2 pi q delta 3 p minus p prime. I hope the steps are clear. Okay. Now you will see why we did that. So what is this now? This is equal to AP exponential of.
Can you please scroll up just a bit?
Yeah.
Just a minute.
Yeah.
Oh, okay. Thanks.
Yeah. So before we figure this out, let's see one more thing. So what is HAP? So this is equal to, so from this commutator, so HAP is nothing but AP, H minus EP vector. Okay. What is H square AP? That is nothing but AP H minus EP square. Likewise, AP dagger will be AP dagger H plus EP. So basically H to the power n AP will be H minus EP to the power n. Okay. Similarly here also. So then what does it mean? This is nothing but exponential I H minus EP t exponential minus IHT. This is equal to AP exponential minus I EPT. Likewise, exponential IHT A dagger exponential minus IHT will be AP dagger exponential I. Is this clear? Do you have any issue in any of the steps? So once we have it, we now know what is the corresponding Heisenberg operator. So phi of x, the Heisenberg operator, is d3p over 2 pi cube. I think, was it too quick? Is it clear to you what I said here?
Yeah.
Huh?
Yeah.
Okay. d3p over 2 pi cube 1 over square root 2ep. Then this becomes exponential minus plus I p dot x. That was already there. Plus a dagger exponential I minus I p dot x. Okay, so this is nothing but exponential minus I p dot x plus a dagger p exponential plus I p dot x. We write just one more step. This is AP dagger H plus EP that is equal to this. Okay. So therefore pi of x is nothing but phi dot of x. See, now we can take this time derivative of phi, but so far when we did the quantization, canonical quantization, we actually didn't find out pi by taking time derivative of the pi because those were all time independent. But instead what we did was we taking an analogy from what we knew about the quantization of simple harmonic oscillator, we wrote down phi and pi. so that they satisfy the canonical commutation relation, that is phi pi commutator is I delta x minus y. So now what will be the canonical commutation then? So we write down the equal time commutator and this commutation relation holds true when t equal to 0. Holds true in both the pictures when t equal to 0. Delta 3 x minus y. Okay. Okay. So now we have the Heisenberg operator and the corresponding conjugate momenta. So this is equal to over 2 pi q. You can see from the first term we will get minus I EP and second term we will get I EP. So if I take minus I common, yeah, go ahead. Someone had something to say. Oh, sorry. I've written phi. Minus I square root of EP over 2. Minus A dagger P IP dot x. Okay. So where P dot x is, so these are with P0 equal to EP. Okay, here also P0 equal to EP. Here P dot x is EPT minus P dot x. Okay, so that's our convention. Fine. And the other commutators vanish as before. Okay, now a natural question to ask in quantum field theory is that if one is outside light cone, that means if two events are separated space-like, then whether the measurement of one event can affect the measurement of the other. Okay, so in order to understand that, what we need to figure out is the commutation between the two the observables that we are measuring. Sorry, what I mean to say is that suppose we want to measure the observable, which is field for us, like the simplest observable that we have is the fields. So if we want to measure this observable, let's say at some space-time location x, and we are measuring the same observable at some other space-time location y, and if x and y are space-like separated, then the question is whether the measurement of this observable can affect the measurement of that observable. Okay, and what do we know? We know that when two operators commute, if that commutator is 0, then the measurement of one cannot affect the measurement of the other, because the order doesn't matter, and so that's what we need to see. So now that we have these Heisenberg operators, let us use those operators to figure out what this commutation relation is. Okay, and then we will see whether that turns out to be 0 for a space-like separated, for two space-like separated events or not. If that is not 0, then it would imply that the theory we have learned for 1 month now is not causal, and which should not be the case.
Hello.
Yeah.
In Heisenberg picture and both Schrodinger, in Heisenberg picture and Schrodinger picture, the difference between the operators are only the four vectors in exponential, right? If it is a four vector in exponential, then it's a Heisenberg picture. Or else if a normal vector product means it will be a Schrodinger picture, right?
Exactly. So there we do not have time dependence. So the time dependence is coming from this term only. So that's why this operator that we have on the left hand side is Heisenberg operator, because it depends on time, space and time.
Okay, so if you want to deal with the questions like space like separation or time like separation, then we want to use only Heisenberg picture, or else we can use.
We want to use the Heisenberg picture. So in order to understand these propagators and all that we are going to deal with now, we need the Heisenberg operator. That's why we need this.
Okay.
Yeah. So what does space-like and time-like mean? Let me first say that briefly. So x minus y whole square, which is nothing but here x and y are four vectors. So this is x0 minus y0 square minus x minus y square. Okay. So when we say space like separated, for space like separation, x minus y square will be less than x minus y square will be less than 0, and for time like separation between two events x and y, x minus y square will be greater than 0. Okay, so it means the two events are inside the light cone, and this means the two events are outside the light cone. Okay, so now what we wanted to compute is this commutator phi x, phi y, d3p, d3p prime.
Can you scroll up a bit?
Yeah.
Yeah, okay.
So this is equal to 1 over square root 4 EP prime okay, then commutation between AB exponential of I, so what's the minus, yeah, plus e dagger B exponential I e dot x, comma AP prime exponential of minus I p prime dot y plus a dagger p prime p prime dot y. Okay, and as you can see that commutation between this and this will survive, and these two will survive. The other two commutators, that is commutation between these two, will vanish and trivial because the same operator. Okay, so this is d3p prime. Sorry, there is a 2 pi to the power 6. AP dagger p prime exponential minus I p dot x plus I why did I write vector here? P prime dot y plus p dot x minus I p prime dot y. Okay, so now we replace these commutators by 2 pi to the power 3 delta of p minus p prime, and then we take this integration over p prime. So I'm not writing that step now, I will just take the integration over d3p prime. So what we get is d3p 2 pi to the power 3, and so p prime will be replaced by p. So we get 1 over 2 EP exponential of minus I p dot x minus y from the first term, and from the second term we get minus of exponential of, we get minus I p dot y minus x. Okay, so these are the two terms we obtained. Now, as it turns out, so we can always sandwich this between the vacuum state, but that wouldn't change what we have done so far. But I'm doing this in order to give it a meaning. Okay, now you see that these are just C number, so 0 0 commutation will be here and that will be 1. Okay, now what is left hand side? So left hand side is actually, okay, so this is equal to 0 phi x phi y 0 minus the ground state phi y phi x. We can also see this, I mean, if we just compute this particular thing, you will see that you will get this first term here. So just a check. Square root of 4 EP prime, and we are taking the inner product you can see that when this A dagger operator hits this 0 gate on its left, that gets annihilated. Likewise, when A operator acts on the 0 gate, it gets annihilated. So the only contribution that we get is when this operator multiplies this particular operator. Okay, and all other terms will be 0. So this is over 2 pi to the power 6. A dagger p prime exponential minus I p dot x plus I p prime dot y. Okay. Now, what is this term? This is the commutator. A dagger p prime AP plus 2 pi cube delta 3 p minus p prime, right? So if we replace that here, this term will again vanish because now AP will act on this ground state, and this term will survive and give us after doing the p prime integration, pi cube exponential minus I p dot x minus y. Sorry, there is no 2 pi cube. I have already cancelled 2 pi cube with that 2 pi to the power 6. So we will be left with this. So this is what I was saying, that this first term is nothing but the so what is this? The interpretation is that a particle created at y is propagating to location x. Okay, and this particular term we call to be d of x minus y, and that is d of y minus x. Okay, likewise, if you calculate the same thing with y on the left and x here, you will get the same thing with y replaced here and x there. So that's d of y minus x. So okay, one more thing. So you remember, right, that this phi of x acting on the 0 gate is interpreted as a particle created at location x. So that's why this particular interpretation works here, that you are creating a particle at location y and that is propagating to another location x, and that is termed as this d or the propagator. But this is not Feynman propagator. As we will see, we will define the Feynman operator as well. But is this clear, whatever we have said so far?
Ma'am, just a minute. If you go through the second step, there is bra 0 and kit 0 here.
Yeah.
But after that step, you are just including the commutator's relationships, right?
Yes.
And then where is the bracket 0 plus 0?
Exactly. So now you don't have any operators here. This is there is no operator. So this bra 0 and gate 0 inner product will be just 1.
Oh, okay.
Yes. Good. Now, okay. Now, our motivation for doing this particular computation was that we wanted to see whether for two space-like separated events, this particular commutator turns out to be 0 or not. So let's figure that out. Okay, so for x and y, space like separated. For time like separated, it must be non-zero. So let's also see that for x and y, time like separated, we will choose a particular thing, we'll make a particular choice. For x and y, time like separated, let's take x0 minus y0 to be t and x minus y vector to be 0. Okay, that's a choice for time like separation, because then x minus y square will be just t square, which is greater than 0. So what happens in this case? So let's analyze this particular term a little bit. Okay, so this is equal to, so we are basically analyzing this t of x minus y. Let me write that down here. So this is t of x minus y. So this is a d3p. This is a 3-dimensional integral. So you all know how to write that down. So this is p square dp, limit 0 to infinity. So in Cartesian it's minus infinity to plus infinity, but we are writing in polar. Then 1 over 2 pi q. So sine theta d theta. Theta goes from minus pi to pi. D phi going from 0 to 2 pi. 1 over 2 EP is nothing but p square plus m square. Then exponential minus I. P0 is EP, and that's nothing but p square plus m square t. Okay. Now, so nothing depends on phi and theta, so we can do those two integrations and we get 4 pi outside over 2 pi cube, 0 to infinity, p square dp, 1 over, there is 1 2 also, square root p square plus m square t. Okay. Now let p square plus m square to be equal to some xi square. So 2p dt is the integration limit. So 1 over 4 pi square m to infinity yeah. So 1 p dp I can replace by xi d xi. Let's cancel out 2 from both sides. So this is xi d xi, and there will be another p left over in the numerator, which we can replace by xi square minus square root xi square minus m square. Okay, and there will be xi exponential minus I t. Okay, these two gets cancelled out, and we have an integration of this sort. So we are not going to evaluate this explicitly, but we just wanted to say that in t tending to infinity limit, for example, this integration will decay as exponential minus I m t. Not really decaying, but oscillating, because there is I in the exponent. But all we wanted to say here is that if these two events are time-like separated, then this commutator is non-zero. So this is not getting cancelled from this. Okay? But if these are space-like separated, let's see what happens. So again we make a particular choice, x0 minus y0 equal to 0, and x minus y equal to, let's say, some r vector. Okay, then what happens to d of x minus y? That is d3p over 2 pi q 1 over 2 EP exponential of, what was it, minus I p dot x minus y, so that means plus I p dot r, right? And what is d of y minus x? D of y minus x is d3p over 2 pi q 1 over 2 EP exponential of this is exponential of I minus I p dot r. Is that clear? Because the same term but y and x interchanged, so that's why there will be an extra minus sign there. Now these two terms are actually one and the same. Why? Because in the second term you can always replace p by minus p, right? So the second term, if we replace this trick we used in one of the earlier calculations, so if we replace p by minus p prime, okay, let me just say that again. So this will become, so minus infinity to plus infinity. If you replace p by minus p prime, you will get d3p prime. One minus sign will appear because of d3p prime. EP will remain same because that depends on p squared, and exponent we will have p prime not r. So in order to interchange the limit, that minus sign will go away and we have d3p, again writing p prime to be p because it's dummy variable. So you see, this is nothing but d of x minus y. So therefore that commutator phi of x, phi of y is equal to d of x minus d of x minus y minus d of y minus x is equal to 0 when x and y are space-like separated. In this theory to show equality of two operators, is it sufficient to show that in both the case expectation value of the operators A, B with respect to vacuum states are equal? Equality of two operators. Why would you show equality of two operators? Well, if you are getting A acting on 0, I mean, let's say okay, so A and B are two different operators, you are saying, right? So let's say one operator is A dagger with momentum P1, that acting on 0 will give you P1 eigenstate up to some normalization, up to some constant, and a different operator will give you a different state. I'm not sure. It may happen that when you are taking the commutation, when you are taking expectation value with respect to 0, what you get there, you get same thing here, but that wouldn't mean that the two states that you have created initially are the same.
I was asking for that that commutator is the operator that which is shown to be 0 in this question. So I was thinking that to show like 0, it is that you have done like expectation value with respect to 0 vacuum state to show that the commutator is equal to 0 operator.
Yeah.
So that I was thinking that to show equality of two operators, we can take expectation value and show like numerically like calculate, compute.
Sorry, compute what?
Compute like this to show equality of operator like if we have to show equality of two operators, we need any arbitrary inner product. Like any arbitrary inner product should be equal if you want to show in.
So no, we are not trying to show equality. Okay, these two propagators. So the physical interpretation here is that the propagation of a particle from x to y and from y to x, if x and y are space-like separated, doesn't matter. I mean, if these two are space-like separated, then sorry, what I said is completely rubbish. So let me rephrase. I'm saying that if x and y, these two are space-like separated, then a propagation of a particle from x to y and propagation of another the same particle from y to x will be one and the same. So that's why this these two propagators turn out to be same, that is d of x minus y, where d of x minus y means you created one particle at y and then that particle is being propagated to another location x. Sorry. That is indistinguishable from one particle being created at x first and then propagated to y when x and y are space-like separated. So that's the claim here. We are not showing equality of two operators. I mean, well, d of x minus y turns out to be d of y minus x. These two propagators turn out to be the same. But notice that this is not an operator. This is a C number. There is no operator here.
I was asking for that. Initially in the question, we have to show that commutator is equal to zero, like commute, like so like commutator is also operator. Like it is, we have to show it is equal to zero operator. So in that you have done to show that we have taken inner product on both sides, like with respect to zero.
The commutator turns out to be not an operator. After you take the commutation relation, all you get is a C number, like a.
Yes, but it has an identity like here. Scalar times an identity.
Yeah,
But this number inner product, we take it comes out number, but before that it is an operator. Like we have taken with respect to zero only. Like if we have to show like it is equal to zero operator, if we want to get a number numeric like a number, we have to show like numerically like with scalars type. So we have to take any two arbitrary cats and sandwich the operator between them. But I was thinking that if you have done with respect to zero, as in this theory, like all operators can be created from vacuum state. So that's why you have done only with respect to vacuum state.
sorry, I couldn't understand your question.
I was saying that if you want to show that commutator of phi x and phi y equal to zero operator, so to show that
Okay, that is true only when x and y are space-like separated,
yes.
as we have shown here.
I understood, but I was thinking that why only like we have taken it to inner product with respect to zero operator only.
Oh, so that is because that's how the propagators are. Okay, that is because phi of x acting on 0, what will it give us? Let's see. So this is equal to integration d3p over 2 pi cube 1 over square root 2 ep exponential of minus I p dot x plus a dagger p exponential of I p dot x acting on 0. Okay. Now this will give you d3p over 2 pi cube 1 over square root 2 ep. Then this acting on 0 will give you 0, and a dagger acting on 0. Remember how we defined our state p, that was square root 2 ep a dagger p on 0. So this is equal to d3p over 2 pi cube 1 over 2 ep exponential I p dot x. And now if you take, so what does this mean? It means you have one particle, you have created a particle at location x. I mean this will be more clear if you take inner product with the momentum, let's say p prime, then you will get what you get in quantum mechanics. So let me just do that and then it will be clearer to you. 2 ep exponential I p dot x p prime. So this is this inner product. So what is p prime p inner product? That is 2 et delta 3 p minus p prime, okay, or p prime minus p, order doesn't matter. So so this is d3p over 2 pi cube there will be a 2 pi cube as well coming from that commutation between AP and A dagger P. So that 2 pi cube and 1 over 2 ET will get cancelled out, and we will be left with exponential I P dot x delta 3 P minus P prime. And what is it? This is exponential I P prime dot x. Sorry, what I showed is in Schrodinger picture. So let me put. So we obtained this particular value. Now you can remember that from quantum mechanics, this is nothing but px commutator, which is nothing but exponential minus p dot x, right? So if you look at these two things now, it implies that this phi x acting on 0 is basically creating a particle at location x. Okay, so that's why we are taking the expectation value with respect to the ground state. This is how we have done the quantization and so on, defined our momentum operators from the beginning. Like momentum operator is 8p dagger acting on the ground state. That gives you, sorry, not momentum operator, the state p, one particle state with momentum p. So that's why when we are writing down the propagator, which means a particle created at location x being propagated to location y, we need to take expectation value with respect to 0, the vacuum. That's how we have constructed. Did I answer your question? Good. Okay. Okay. Now that we have explained what this commutator is,
Ma'am, just a minute. Can you go back to the final answer of the integration that you have done for a space-like integration? Commutator.
Yeah. Is it?
Yeah.
Yeah.
At last you said that e power I m t.
This one?
You came to the conclusion, right? It's an oscillatory function.
Exponential IMT.
Yeah.
Here? Okay.
Here. Yeah. How did it turns to e power I m t at last? Because e power I, how they eta turns to m.
Yeah, we are writing down the lower limit because as t tends to infinity. Okay, so here we are. So when you put t, so this xi limit goes from m to infinity, and the lower limit we are putting here just to show that that is one value. I think we can take any other value, but the fact is that as t tends to infinity, so this is a polynomial, like it goes as xi, whereas this is exponential. So in the t tending to infinity limit, that dominates. So that's why we are just writing that down. But we are just writing that exponential factor down with the value m that we know. I think that's all there is.
Why we are considering t as a limit? Because here the integral runs from integral is for eta, right? Why we are considering on t?
So okay, so this is, so t is, I mean, the way we have taken the separation. So x0 minus y0. So doesn't matter how long t is. I mean, doesn't matter how much distance apart the two events are happening, not distance, how much time apart that the two events are happening, whatever you are getting for this propagator from y to x, that will turn out to be exponential minus IMT. That's the meaning.
Oh, okay.
Yeah. Yeah. Then, where were we? Okay. So far we have done this. Let me just tell you the Feynman propagator now, and then we'll stop. So the Feynman propagator is defined as follows. So this will be useful. So we now define it, and then later on might be useful to us. So this is d of x minus y that we have already shown when x0 is greater than y0, and d of y minus x when y0 is greater than x0. Okay, so this is nothing but the time ordered product, expectation value of time ordered product of phi x, phi y. Okay, where t of phi x, phi y, this is equal to phi x, phi y when x0 is x0 is greater than y0, and phi of y, phi of x when y0 is greater than x0. Okay, so time ordering means that if y is happening at an earlier time, it should be put to the right, and the event that is happening at a later time, that should be put on the left. So here y0 is greater than x0, that's why phi y appears on the left. So that's all this. So this is time ordered product. Okay. Now there is a integral representation of this Feynman propagator. Now how that integral representation is actually turning out to be this d of x minus y when x0 greater than y0 and d of y minus x when y0 greater than x0 is what we will see in detail. Okay, so let me just write down the integral representation first. So the Feynman propagator is d4p over 2 pi to the power 4 I divided by p square minus m square exponential of minus I p dot x minus y. Okay. Yeah. Now note one thing, that we are writing d4p instead of d3p now. So far whatever momentum integration we had been writing, it was d3p everywhere, and even in the Heisenberg picture it was d3p, but exponential was exponential I p dot x, but that p0 was fixed to EP coming from the dispersion relation. But now for this Feynman propagator, first time we are writing d4p, where p0 is also an integration variable, it is not fixed to EP or something. Okay. Having said that, now let's see. So more explicitly, this is d3p over 2 pi cube integration dp0 over 2 pi I over p square minus m square e dot x minus y. Okay, and what is that contour? So the contour that we need to choose in order to get this thing is as follows. So the contour is this is imaginary p0 plane. This is imaginary p0 plane. So this is a real p0 axis and this is imaginary p0 axis. Okay, and yeah, one more thing you note that this integral, the integrand is having poles at two locations in the real p0 axis, and the two locations are, so when p square minus m square equal to 0, that occurs when p0 square is equal to plus minus square root p vector square plus m square, which is nothing but plus minus ep. Okay, so at these two locations the there is pole for that integrand. So this is minus ep and this is plus ep, and the contour that we need to choose is like this. Okay, so this is the contour. Now how this contour works, let's see that explicitly. So when x0 is greater than y0, so that means this integral representation of the Feynman propagator that you have written down, that should boil down to d of x minus y. Basically that should boil down to this particular integration, this particular, what is that? Yeah, this particular left hand side. Okay, so okay, so when x0 greater than y0, how would you close this particular contour? Would you close it in the lower half plane or in the upper half plane? Can someone tell me? How would you close this contour when x0 is greater than y0? So the trick is you need to look at this exponent. See what is exponential minus I p dot x minus y, that is equal to exponential I p0 x0 minus y0 plus I p dot x minus y. Okay, now when x0 is greater than y0, that means this is a positive quantity, this is greater than 0, and we need to close the contour in that plane where the integrand will go to 0. So if p0 equal to, let's say, plus I infinity, okay, then what will happen to that term? It will become exponential of infinity then x0 minus y0. So that is becoming infinity, right? So we cannot close this contour in the upper half plane because there p0 is going to plus I infinity. So the choice that the contour, so basically we need to close the contour in the lower half plane, because there, so if we choose p0 to be minus I infinity, of course it is becoming exponential minus infinity x0 minus y0, so that is becoming 0. So we close the contour. So when this is the case, x0 is greater than y0. So let us complete our contour. Okay. So the contour should be closed this way. So the pole that is inside the contour is this one plus EP. So that means you evaluate that integration over dp0 over 2 pi I divided by e square minus m square exponential of minus I p0 x0 minus y0 plus I p dot x minus y. What is the value of this contour? So this is equal to 2 pi I times residue at p0 equal to plus ep. And how do we calculate the residue? And one
Just
more
a
thing.
moment.
Yeah. Go ahead.
Why can't we draw the contour in such a way that both the residues come into that contour? Such a way that
we are
both the
choosing-
yeah. minus EP and plus EP is the jump is in the upper side.
Yeah. So this contour choice has been made so that this particular integral representation boils down to what we want. If you choose any other contour, then for x0 greater than y0 you will not get d of x minus y, or for y0 greater than x0 you will not get d of y minus x. So you could have chosen the contour to be like here and then that way and this way. So that will not give you Feynman propagator, that will give you something else which is called advanced propagator. The definition is a bit different, but in order to get Feynman propagator, which is defined in this particular way, the contour that you can only choose is this one. Of course, with the convention that I p dot x is I p0 x0 minus p dot x. If you choose the other convention, meaning this one where we most positive sign, then the contour should be chosen this way and that way. But for the convention that we have chosen for our metric, that is g nu is +1 and then minus for the space like spatial directions. This is the only contour that will give you this thing, d of x minus y when x0 greater than y0 and d of y minus x when the other way around.
Okay.
So right now, so we have already written down the momentum, the integral representation. Right now what we are trying to show is that this particular contour is indeed giving you d of x minus y when x0 is greater than y0. Okay, so we're justifying what we have already said. So see, now for this x0 greater than y0, we have the contour that we have now is actually clockwise. So this is clockwise rotation. So that's why there will be another minus sign coming due to the clockwise contour. So this is minus 2 pi I, and residue is limit of p0 becoming ep, p0 minus ep I divided by p0 minus ep plus ep, then the exponential okay. So this gets cancelled out and we replace P0 by EP. There is I here and minus I there, so we get 2 pi exponential minus I EP x0 minus y0 divided by 2 EP plus I P dot x minus y. Okay, so the entire integral was there was a d3p over 2 pi q. d3p over 2 pi q this minus coming from due to clockwise contour. Okay. Oh, I'm running out of space. Right, so there was a 2 pi here in the denominator, so let me put that. So that 2 pi gets cancelled out with this 2 pi and we are left with d3p over 2 pi q. So this is over 2 pi q 1 over 2 EP exponential minus I p dot x minus y, but with p0 being fixed to plus EP. Okay, and that is nothing but our d of x minus y that we figured out, which is okay. So this is when x0 greater than y0. Now you can check by yourself that when y0 greater than x0, will be d of y minus x. So choose the contour appropriately, because now you know you need to choose contour in the upper half plane for that case, and then check it explicitly that you are indeed getting d of y minus x. Okay. So let me know if you have any questions. Okay, good. If not, let's meet next week.
Can you just scroll down a bit?
Yes.
Ma'am?
Yeah.
Hello.
Yeah.
Actually, I have a question regarding the final exam.
Yes.
Actually, I just registered for 2 courses. One is accelerated physics, another one
Sorry,
is
I can't hear you. Can you speak up a little bit?
Am I audible now?
Yes.
Actually, I registered for 2 courses. One is accelerator physics and another one is this QFT. Both are having the exams in the same date. So what am I supposed to do now?
You should write to NPTEL moderator.
Okay, can you give me the mail ID of the person?
I have no idea, but maybe I'm not sure. I don't have the mail ID. Sorry, but what you can do is write on that discussion forum that you have probably on the NPTEL portal.
Okay, sir.
Yeah, maybe the TAs will do something. I'm not sure.
Okay.
Yeah.
Thank you. Can you please forward this thing to the officials from your side also?
Sorry, forward.
Can you forward this message to your higher officials from your side also? It will be faster, I think. The reply will come faster.
Okay, I'll see whom should I talk to. Yeah.
Oh, thanks.
Yeah.
Okay, thanks. I got it.
Okay, good. Okay, so let's stop here.
Thank you. Bye.
Yeah, bye.